The pendulum we looked at before had all of its weight concentrated in the end, and we could really ignore any mass between the end of it because it was on that lightweight string. You can't do that for most pendulums. Let's look at this stack of rulers. It has its mass evenly distributed all the way up and down. But if we give it a push, its motion is also periodic. And we'll see that it actually is simple harmonic, but we have to take into account the distribution of mass. We call this a physical pendulum. So I took this meter stick and made it into a physical pendulum. There's a little hole very close to the top, 1.5 centimeters away, and I let it pivot back and forth on that. And I wanted to come up with an equation for its period and then check that. The simple harmonic motion part of this is not very tricky. It's rotational motion, so I started with the sigma torque equals I alpha version of Newton's second law. I said the torque caused by gravity is the only torque. Torque is RF sine theta, and in this case it's the force of gravity. What's R? It's the distance gravity acts from the pivot point, which is the distance the center of mass is from the pivot point, which in this case is about 0.5 meter minus the 1.5 centimeters to the hole, so 0.485 meters. I subbed in mg for the force of gravity, and I'm going to use that same approximation that we used for a simple pendulum. I'm going to say as long as I stay at small angles, sine theta and theta are about the same. So we get an equation that fits our pattern for simple harmonic motion. Minus constants times theta equals constant times the second derivative of theta. I've got my theta. I got alpha, which is its second derivative. As always, I just plug back into what we got from our torque or force equation. Most of it all cancels, and there's the equation for period of a physical pendulum. The only thing tricky here is figuring out what is I. So that's what the math is over here. So I do the integral we do for moment of inertia. It's a uniform stick, so I say the fraction of mass is the same as the fraction of length. I solve for dm. I get my integral. My lower limit is minus 1.5 centimeters, or 0.015. My upper limit is 98.5, or 0.985. Take the integral and I plug in all my numbers, and I get a number. So now I plug that number in with everything else, and I come up with a period of 1.63 seconds. I then check it in lab, and I was pretty close. So that's 16 seconds for 10 back and forths. I'm happy with that. So physical pendulum, it's very similar to how we do any other type of simple harmonic motion. The only tricky thing is sometimes getting the moment of inertia. But the simple harmonic motion part of it should be very familiar at this point.